Hello and welcome to a lecture on linearity. I'm Steve Ellingson. Here's an overview of this lecture. Previously, we described two ports in terms of three quantities. We described them in terms of gain, we described them in terms of their impedance, and we described them in terms of the internal noise in which they generate, typically as the equivalent noise temperature or as a noise figure. Now we consider a fourth consideration, and that is linearity. So linearity will be yet another property of two ports. First, we'll describe the linearity concept, which you hopefully already have some familiarity with, but will put you on firm footing. I'll discuss the specific concept of memoryless polynomial response, which is a particular way to characterize linearity of two ports. I'll talk about third-order systems with sinusoidal, that is single-tone stimulus. So these are systems in which we apply this model in a case where we have a single RF tone applied to the input. And that will result in two concepts. One is gain compression, and the second one being 1 dB compression point, both ways that we can characterize the linearity of systems. Then we'll talk about third-order systems with two-tone stimulus. So in this case, we'll be applying two tones at a time, and that will result in the concepts of intermodulation and also second and third order intercept point. This will also lead to another concept known as the beat product. I'll talk about AM to PM conversion, that is, the conversion of amplitude modulation to phase modulation as a result of the limited linearity of systems. And then finally, I'll talk about the linearity of differential devices. So first, the linearity concept. Linearity means response is independent of input. So if we have some input x, and let's give it a subscript x1 here, then we get y1 as an output. And perhaps y1 is some transfer function, we'll call it big F, where x1 is an argument. If the system's linear, then if we apply some other input, then we can compute the new output using the exact same transfer function. In other words, the response is independent of the input. F here does not change as a result of x1. x1 is simply an argument that's applied to this functional relationship. We sometimes use the concept of superposition to define what we mean by linearity. And what we mean there is something a little bit more specific. So in this case, if we say we have some input x1, we say that the output is some constant, we'll call it A, times the input. And then if we have some other input, x2, then we can compute its output as A x2. So here we're just applying this previous concept, the independence of input. But now having this, we come up with another result. This is the superposition result, in which if we apply the sum of these two signals, then we can compute the new output as simply A x1 plus x2. And that's what we mean by superposition. If we have any one or two results, then we can immediately compute the response to linear combinations of those inputs. And the consequence of this then is that the output is not simply independent of the input, but it's also proportional to the input, because this A is assumed to be some constant. Now, we frequently assume that simple components such as resistors, such as capacitors, are perfectly linear. In other words, if we have some C for a capacitor or some R for a resistor, that C or R, that value, is independent of the voltage or current that's applied to that component. And often that's a safe assumption. At very high power levels, we may have to take into account that these values of capacitance or resistance are themselves functions of the input, and that will lead to AM to PM conversion, but we'll return to that a little bit later in the lecture. In fact, most passive components can be assumed to be linear, except when we approach these high power conditions, the kind of conditions we typically see in power amplifiers, for example, and less so for gain amplifiers and other devices where we're not operating at powers on the order of watts or greater. Now there's some components that we work with routinely that are definitely nonlinear. One important example, of course, is transistors. Now often it doesn't seem like we're accounting for the nonlinearity of transistors, because if we were going to use a transistor as a linear gain device, then we try to find a operating point around which the transistor behaves in an approximately linear fashion. However, just to underscore the fact that they are fundamentally nonlinear, just recall, for example, for bipolar technology, we have that the collector current is dependent on the base emitter voltage through this relationship, which is fundamentally exponential. That is not linear. It only seems linear because we constrain the range over which the input, VBE, can vary, and over that range, IC varies in an approximately linear way. In other words, the exponential behavior here is not apparent. It seems approximately linear. But of course, as VBE gets large enough, then we have to account for that nonlinear behavior. Similarly, for a FET, recall that the drain current is a function of the gate source voltage, and that relationship is a squared relationship. So again, we choose operating points so that this squared relationship looks approximately linear, and that requires constraining the range over which VGS can vary. But inevitably, if we go to higher and higher powers, we will eventually see or eventually perceive the nonlinearity, and we'll have to account for it. So one way to go about doing this is to invoke a concept known as memoryless polynomial response. And what that means is we assume that the output of the device, this could be a voltage, it could be a current, is given by the input x of t, which again could be either a voltage or a current, through a polynomial response. So x is the input, y is the output, and the relationship between the two is given by this polynomial, where we see some constant plus the input times a constant plus the input squared times a constant times the input cubed times a constant, and so on, up to potentially any number of terms. Now that's what we mean by polynomial. What we mean by memoryless is that the output depends only on the current value of the input. It doesn't depend on the input a millisecond ago or a microsecond ago. It depends only on the current value of the input. Now let me just comment briefly on these assumptions. The polynomial response model is pretty good, and the reason is because we have this concept known as the Taylor series. The Taylor series says that any function around some central value can be described as a polynomial, and the important coefficients are typically the low order coefficients, and by the time we get up to a sufficiently high indexed coefficient, the values become small. So the polynomial response assumption is usually pretty good. The memoryless response assumption is either good or bad depending on the application. What happens at very high power levels is that devices which become nonlinear in a way that is time dependent as well as input dependent. So for example, if you drive an amplifier very hard into compression, it may remain in compression for some period of time even though the signal level has dropped back down. However, if we proceed here with the assumption that that kind of problem is not apparent, then we can use this model, the memoryless polynomial response model. Again, the input and output, x being the input and y being the output, can be any combination of voltage and current. So x could be a voltage and y could be a voltage, or x could be a voltage and y could be a current, or x could be a current and y could be a voltage, and so on. Also, this whole model works regardless of whether the two-port is single-ended or differential. This is a minor issue. In fact, we'll return to this as the last topic in this lecture. Now this captures memoryless nonlinearity. Again, linearity in which any change in the response to input is instantaneous. Once power levels become sufficiently high, then the response becomes time varying, and we have to account for that. And that's typically only a problem for things like very high power amplifiers. The coefficients are constants describing the system. So once we decide that this model is appropriate, then we can describe the system, that is the two-port, using this set of coefficients. So A0, A1, A2, A3, as far as we want to go. And that set of coefficients then are time invariant and describe the system for all time. So we can use this response model to now define more formally what we mean by linearity. A formally linear system then becomes simply one in which only A1 is non-zero. In other words, A0 is 0, A2 is 0, A3 is 0, and so on, so that the output is simply the input times some constant. Now I should make an important point. Usually what we have in a system is not just this, but we also have this leading term, A0, this constant right here. And we commonly refer to that as a DC offset. Now, this is inevitable in systems. We always have some DC leakage, or we have some offset that we're introducing, for example, as a result of transistor biasing. And even though it's there, we typically choose to ignore it and still call the system linear, as long as A2, A3, and so on are 0. And one reason for this is DC terms can usually be eliminated by filtering or made irrelevant by AC coupling. So the fact that this A0 here is non-zero is irrelevant because we end up filtering it away, or we just make it irrelevant because we do AC coupling between stages. Most systems are well described by coefficients up to third order and neglecting higher order coefficients. So typically we can assume that A4, A5, A6, and so on are 0. Now that's not universally true, and certainly at very high powers you need to include higher order coefficients. But for most work, in fact I would say more than 90 to 95% of all work that's ever done in RF engineering, where linearity is a consideration, we can get what we need done simply by assuming that only A0, A1, A2, and A3 are non-zero, and assuming A4 and so on are 0. In some cases of practical interest, again, coefficients of order 4 or greater become important, and again, those are typically power amplifiers. Okay, so here's a quick example just to show you how this model can be applied. So in chapter 10, we found the relationship between the collector current, I sub C, and the base voltage, V sub B, or I could say V sub BE, just to be more specific if this is a common emitter amplifier, can be written in this form. That's the equation I just showed previously. In this form, this thing here and V sub T are constants, right? V sub T is the thermal voltage, and I sub C naught is a constant. So I could ask you to develop a memoryless polynomial model for this particular amplifier that's using this particular transistor. And the way to do that is to use a Taylor series, and here's the details of how that can get done. I'm not going to go through this in detail, but just to give you an outline of how this works. The Taylor series for an exponential looks like this. Then I get a series that looks like this, and then I can identify the coefficients A0, A1, A2, and so on, and I see that they have this form. So it's a very simple thing to do. As I pointed out before, we will have a term A0, which is non-zero, so it's formally nonlinear. However, it doesn't really matter because we're typically not interested in the absolute current. We're interested in the small signal current. That is the current around the bias point, and that is precisely that expression when A0 is 0, so that the small signal current, I sub C, is simply the same polynomial model with A0 ignored. So here's an example of how we can compute those values. An important case to consider is this third order model. Now I'm ignoring all coefficients A4, A5, and so on. I apply a sinusoid. So in this case, x sub t is the sinusoid A. That's a constant, cosine omega t. So it's just a single frequency sinusoid with magnitude A. So I make that substitution. I get 4 terms. Those terms all have cosine omega t, or cosine 2 omega t, or cosine 3 omega t in them. 2 of the terms are cosine omega t, so I can combine those. So I get a total of 3 terms. So what we see is that whereas we started with an input that has simply 1 frequency in it, the output has 3 frequencies, namely omega, 2 omega, and 3 omega. So these terms have special names. The first term, which has the expected frequency in it, is referred to as the fundamental. The second term, which is twice the frequency, is referred to as the second order harmonic. And no surprise here, you see the second order harmonic depends on the coefficient a sub 2. And the third term, which is at 3 times the frequency, we refer to as the third order harmonic. And again, you may not be surprised to see that that depends on the coefficient a sub 3. If we go back to the fundamental, we see that the fundamental depends on a1, because that's the linear contribution, or that's the linear output that we expected. And then we also have this additional contribution, which depends on a3. So interestingly, when we have a third order model and we apply a sinusoid, we see that the fundamental depends not just on the linear response, but also on this additional term, which is dependent on the value of a sub 3. So that brings us to the idea of gain compression. So the way to understand that is in terms of the plot I've shown here, where the x-axis is simply the magnitude of the input, and the y-axis is simply the magnitude of the output. And if this is a perfectly linear system, we would expect that the relationship between these two is a perfectly straight line. So this is the ideal linear transfer characteristic. In other words, this is what we get if we have only A1 and not A2, A3, A4, and so on. And the fact that this goes through the origin just means that A0 is 0 here. Now, if we have any nonlinearity at all, in other words, if A3 is not equal to 0, then what happens is we have a deviation from this perfectly straight characteristic. And what typically happens is that the deviation is downward. And this is exactly what we mean by gain compression, is that instead of getting this ideal characteristic at high input levels, we instead get some lower level output than what we'd expect. So down here we see that the difference is very, very small, and we would say we're not in compression down here. But as the level grows and grows, eventually we see significant amount of compression and a significant deviation from the ideal transfer characteristic. Now, one way to characterize gain compression is in terms of this quantity known as the output 1 dB compression point. So what we do is we look at the difference between the ideal transfer characteristic and what we actually get out, and at the output level where that difference is 1 dB, we call that the output 1 dB compression point. And then the corresponding input level we refer to as the input 1 dB compression point. Now I just want to point out here, there's nothing magical about 1 dB here. It's simply an arbitrary criterion for deciding what is significant compression. So don't read too much into this value of 1 dB. It's simply a common way to characterize this overall deviation. Now, let me point out also that the idea of 1 dB compression applies regardless of whether you have a third order system or not, and applies regardless of whether you have just a single tone or not. In other words, you can compute a 1 dB compression point for 2-tone input or 3-tone input. So again, this is not specific to the third order memoryless polynomial system model. However, if I do know that I have a third order model with sinusoidal input, I know the fundamental looks like this. Of course, there are higher frequency terms, but we're not interested in those at the moment. We're just going to pay attention to the fundamental. And we know the fundamental consists of a linear gain term, in other words, what we would get if we were perfectly linear, and then a compression term. Now, this is really only compression if A3 is negative, right? If A3 has a sign which is negative, then we get this particular characteristic. If A3 were positive, we would get the opposite curve. We would get something that looks like this. However, most systems are compressive. In other words, they lose gain at higher power levels. And this is approximately true for the vast majority of RF devices that are commonly encountered, both active and passive, and regardless of stimulus. Just here I'm showing it for the third order case. Now the 1 dB compression point. Again, 1 dB compression point is a perfectly general idea. However, if we think about how this works for a third order system, and we write the fundamental like this. Again, we're just neglecting the higher order terms. We can compute the 1 dB compression point. That's simply the point where this thing here, the magnitude of that value, is in dB 1 dB less than what we get from just the linear term by itself. Right? So this is a equation which we can solve to determine what value of A gives us the 1 dB compression point. So we'll call that value A sub 1 dB. We can solve this equation to figure out what that is. So it turns out the input 1 dB compression point is approximately equal to the square root of 0.145 times the magnitude of the ratio of A1 to A3. So what we see is that as A1 gets bigger and bigger, the 1 dB compression point gets bigger, but as A3 gets bigger and bigger, that 1 dB compression point gets smaller and smaller, which is exactly the behavior you'd expect. And again, remember this equation applies only to the third order polynomial nonlinearity model with sinusoidal input. Now from that we can immediately get the output 1 dB compression point. It's simply the input 1 dB compression point times the magnitude of A1, because that's the linear gain. So again, I'll point out a common pitfall here, forgetting the assumptions that have been made to get these expressions. Again, third order nonlinearity, memoryless, sinusoidal input. If you have those three things, then these equations apply. But to the extent that the system is not third order, or to which the signal looks different from a sinusoid, these expressions do not necessarily apply, and you have to be careful. Now, the previous slides show this in terms of voltage and current, right? I said A or X could be either voltage or current, and Y could be either voltage or current. It really doesn't matter as long as you agree what you mean by X and Y. But frequently we're not interested in voltage or current. What we're interested in is power. So all these things can be expressed in terms of power as long as we're clear about the impedance assumed. Remember, voltage and current are unambiguous, but when we talk about power, we've made some assumption about what impedances we're talking about. So as long as we're clear about what impedance we're operating at, we can immediately get power, because once we have impedance and voltage, we can get power, or impedance and current, we can get power. So for example, the output referred 1 dB compression point is expressible in terms of power, and typically that's given a variable such as P sub 1 dB. Sometimes it's written P sub 1. Sometimes it's written OP sub 1, where O is output. And this is typically what you get in data sheets. So frequently data sheet for a transistor, for an amplifier, will specify the output referred 1 dB compression point, the point which the output power is 1 dB less than what you'd expect from a linear gain amplifier, and at the impedance that you're supposed to be operating this device at. For input referred 1 dB compression point, we typically use a variable such as P sub 1, I for input, and that's simply the output 1 dB compression point divided by the linear gain, where G here is linear gain. And that's actually what's relevant for most receivers. So typically manufacturers, data sheets will give you output referred 1 dB compression, typically because it's higher, but also because it's what you would use for a power amplifier or for a transmit device. But if you're interested in receivers, typically you're more interested in the input referred 1 dB compression point, and that's simply the output 1 dB compression point divided by the linear gain. Sometimes you want to know what a bipolar transistor is capable of doing. If you have a bipolar common emitter amplifier stage, a useful rule of thumb is as follows, and this is all it is. It's just a experience-based rule of thumb. If the collector current is about 20 milliamps and the output impedance is about 50 ohms, you typically find that the output 1 dB compression point is about plus 10 dBm. That's 10 milliwatts. Now again, that's just a rule of thumb. Some transistors do better than this, some transistors do less, but typically it's in that ballpark, within 3 or 4 dB. If you need to increase the 1 dB compression point, then the way you do that is by increasing the collector current or increasing the impedance. And similarly, if you do something to decrease the collector current from 20 milliamps or decrease the output impedance from 50 ohms, you typically find that this goes down. I'll tell you that FET common source amplifiers tend to do a little bit less well than this. There are lots of ways that you can make FETs work better or worse than that, and there's lots of ways that you can make bipolar common emitter amplifiers work better or worse than this.